All right, hopefully y'all can see that. So solutions, remember, are our synonym for homogeneous mixture. Uh, so it's one of the two kinds of mixtures, homogeneous, heterogeneous. Homogeneous mixture is a synonym for solution. Um, Sometimes you'll hear aqueous solution, and all that the aqueous means is it means the solvent is water. So we should talk about a couple terms when it comes to solutions. So the thing that does the dissolving, that's called the solvent. So if we have an aqueous solution, the solvent would be water. The thing that gets dissolved, that would be the solute. So if I am making like a saline solution, right? Okay, my solute would be sodium chloride. Okay, so that's the thing that gets dissolved. And then once the solute is fully dissolved in the solvent, we have a solution. So the solute and solvent together make the solution. In general, the solvent is the bulk of the solution. Usually there's more solvent than thing that's dissolved. That's not always the case, but that is usually the case. If something dissolves, we say it's soluble. And if something does not dissolve in a solvent, we say it is insoluble, so not able to dissolve. If something dissolves in water, if something is soluble in water, we say that it has entered the aqueous state. That's what the little AQ means. Sometimes you'll see that in reactions. We'll be writing that a bit here in a moment. So that means aqueous. That means currently dissolved in water. Right? I don't know where else to put this electrolyte thing. It's always a weird thing. Where do I put electrolytes? An electrolyte is a substance that when it dissolves in water, allows that solution to conduct an electric current. You've probably heard of electrolyte like with Gatorade, right? Okay, really a terrible term because an electrolyte, salt water is an electrolyte. That's not going to be very hydrating. Okay, so I don't know why Gatorade chose that term. But anyway, an electrolyte is technically anything that dissolves in water and then allows it to conduct an electric current. And there's three things that can dissolve in water and allow it to conduct an electric current. They are soluble ionic compounds. We're going to talk about how you can determine if if an ionic compound, a salt, is soluble or not in a moment. And then there are 6 strong acids that are strong electrolytes fully dissociate, and there's 12 strong bases that fully dissociate. We're going to talk about 2 and 3 if you take Chem 102. If you don't take Chem 102, then you may never get to those because acid-based stuff is usually covered in Chem 102. So tonight we're going to focus on soluble and insoluble ionic compounds. There are other things. I mean, a substance that does not fully dissociate or something that, when you dissolve it in water, only produces a few ions. That's called a weak electrolyte. And then there's even a classification of substances that dissolves in water, but does not conduct electric current. And those are called non-electrolytes. Non-electrolytes are sugars or alcohols, and they dissolve by a different mechanism. So we didn't get to intermolecular forces, okay, yet. But sugars and alcohols are able to dissolve with the water using hydrogen bonding. They don't break up into ions. So it's just a different mechanism for them to dissolve, which is why they don't conduct an electric current. Cool. Ionic compounds, and we're going to get into this more detail when we get to intermolecular forces. Ionic compounds, what allows them to conduct an electric current is when an ionic compound like sodium chloride dissolves. Water breaks it up into its ions. So you get a sodium ion, you get a chloride ion. If you've taken high school chemistry before, you may know that water is polar, right? And that's how water is able to do this. If that doesn't make any sense to you yet, that's okay. All right, we didn't get to Lewis structures. We haven't talked about polar or nonpolar, but the partially negative oxygen ends of water are able to stabilize the cations, and the partially positive hydrogen ends of water are able to stabilize the anions. And that's what allows this thing to become separated and yet still be stable. It is these ions that allow for electrons to be shuttled throughout the solution. So that's what allows that electrical current to be conducted. Cool. How do you know if a substance is going to dissolve? Well, that's where we need to use our solubility rules. I'm gonna pull that up here right now. Maybe. There we go. She's loading. I passed this out last night in lab, so grab your copy. We got to add a couple things to it. You do not need to memorize this. When I was in high school, they made us memorize this, and now they're just getting soft these days. I tell you. So I had to know the Latin. I had to memorize this stuff. Now they're not even, we just got an email. They're not even giving midterms and finals in high school anymore. You got to do it in class. It's like, give me a break. Tell you, these kids getting soft. Anyway, uh, this table is how we determine whether or not a substance is going to dissolve in water, whether or not a salt, an ionic compound. So salt is a synonym for ionic compound, metal, not metal. This is how we determine whether or not a salt's going to dissolve in water. So these are the simple solubility rules for that. And we are going to add some things. But the first thing I want to mention is that this is ranked in order of importance. So you always start with rule 1, and you go down through the rules till you find the first rule that applies, and then you stop reading. So you start with rule 1, okay, and you progress down through the rules, okay, until you find a rule that applies, and then you do not keep reading. And the reason you don't keep reading is if you were to keep reading, a lot of times it would like contradict itself. Okay, like they are ranked in order of importance. So let's start with rule 1. I need you to add a couple things. Here we go. So hopefully you got this out in front of you. Rule 1 says most nitrate salts are soluble. And that means if the compound contains a nitrate, it's going to dissolve. We're going to add 2 things to this. We're going to add most nitrate acetate, which is C2H3O2 minus, and chlorate, which is ClO3 minus. Salts are soluble. So I want you to add to the top rule here. I want you to add most nitrate, acetate, and chlorate salts are soluble. So we're adding 2 additional ions here. So if your salt has got nitrate, acetate, or chlorate in it, then it's going to dissolve in water and you can stop reading. But if your salt does not have nitrate, acetate, or chlorate in it, you got to keep reading. Rule 2 says this. Rule 2 says if your salt contains an alkali metal, which is group 1, right? Make sure we know those family names. If your salt contains an alkali metal, lithium, sodium, potassium, rubidium, cesium, francium, or the ammonium ion, NH4+, which is our only polyatomic cation, it's special, then it's also going to be soluble. So if you have an alkali metal or an ammonium ion, you could stop reading, and this thing is going to be soluble. It's going to dissolve. It will enter the aqueous state if you put it in water. Rule 3 is the first one where people start to get confused, and you don't need to get confused. Let's talk about what Rule 3 says. Rule 3 says if your salt contains a chloride, bromide, or iodide, then it's going to dissolve in water. However, notable exceptions would be chlorides, bromides, and iodides that are silver, lead, or mercury 1. Mercury 1 is a weird diatomic cation. You don't even have to worry about that. I ain't going to put no mercury 1 salt on there. Okay, I'm really interested in the silver and the lead. So here's what this says. It says if you're, I don't know, iron 3 chloride, you going to dissolve, right? If you're Fe Cl3. Rule 1 does not apply to you. You are not a nitrate, acetate, or chlorate. Rule 2 does not apply to you. You do not have an alkali, earth metal, or ammonium cation. But Rule 3 does apply to you. You have a chloride. And chloride salts are soluble unless that chloride is paired with silver, lead, or mercury. That ain't silver, lead, or mercury. It's going to be soluble. This would enter the aqueous state. If something is soluble, we write AQ for aqueous state. It will dissolve. However, if I had PbBr2, this guy is going to be an exception to Rule 3. First, we look at Rule 1. This does not have a nitrate, acetate, or chlorate. Then we look at Rule 2. It does not have an alkali, earth metal, or ammonium cation. Then we look at Rule 3. It's a chloride, bromide, or iodide. We got a bromide. However, this is not going to be soluble because the bromide is paired with lead 2. That's one of the exceptions. If you put lead 2 bromide in water, it will sink to the bottom. It is not going to dissolve. What does that mean? Well, that means it's going to stay a solid. And we actually show that. We write S for remains a solid. It will not dissolve or enter the aqueous state. So hopefully you see how the exceptions work, right? If you're silver chloride, silver bromide, silver iodide, lead 2 chloride, lead 2 bromide, lead 2 iodide, don't worry about the mercury. But if you're any one of those 6 salts, you are not going to dissolve. Rule 4 has got has got our sulfate rule, and this says most sulfates are soluble. And once again, we have 4 exceptions. The only sulfates that are not soluble: barium sulfate, lead 2 sulfate, mercury 1 sulfate, and calcium sulfate. They are not going to dissolve in water. They will not dissolve in water. Rule 5, we get to abbreviate quite a bit. In Rule 5, we're going to change this to most hydroxide salts are insoluble. I want you to change this to insoluble. This set of rules got a lot more detail than we need in Chem 101, so we don't need to worry about the slightly soluble thing. We're going to change it to insoluble, and then you can cross out the rest of this rule. It's pretty sweet. So you don't need that level of detail with the marginally soluble stuff. Same thing here in Rule 6. We're going to make a slight change. Rule 6 says most sulfide, carbonate, chromate, and phosphate salts are only slightly soluble. Again, we're going to change that to insoluble. Insoluble. So hopefully you made those changes on your sheet. Okay. Yeah, now we just need to practice. Let's do this thing. So hang on here, folks. Let's see. Oh, that did not. Oh, it did adjust. I almost can't believe it did that. Zoom is getting better. Can't believe I just said that. Hang on, folks. We're going to try and do a double screen share. This is going to be crazy. I think it may have worked, but I lost my writing, didn't I? Dang it. That's okay. It's going to be all right. All right, folks, here we go. I would like to use the solubility rules, and hopefully you can see both of these things on my screen right now. And I would like to predict the solubility of these 6 salts in water. Let's do a couple together, and then I'm going to turn you loose on it to try it. So my first salt of interest is sodium chloride. I want to know, will it dissolve in water? So we are going to start here at rule 1. And we are going to stop reading, excuse me, when we find the first rule that applies. So sodium chloride, does that contain a nitrate, acetate, or chlorate salt? Nope. On to rule 2. Most salts containing lithium, sodium, potassium, cesium, rubidium, the alkali metal ions, or ammonium are soluble. Do we have an alkali metal ion or ammonium? And the answer is, there's the sodium. This says it's soluble. We're going to write AQ here because that bad boy would dissolve in water and enter the aqueous state. Take a look at number 2, calcium nitrate. We started rule 1. Does calcium nitrate contain a nitrate, acetate, or chlorate? Yeah, then it's soluble. So we're going to write AQ here for that guy. I want you to try 3 through 6. Give these guys a shot. Tell me if they're soluble or insoluble. 3 through 6. All right, number 3, silver chloride. Rule 1, does rule 1 apply? No, no nitrate, acetate, or chlorate. Rule 2, does it apply? No, no alkali metal ion or ammonium ion. Rule 3, does it apply? Most chloride, bromide. Yay, we got a chloride. It's soluble, right? Wrong. It's an exception. It's silver chloride, so that guy's going to be insoluble. You're going to put an S there for solid. Number 4, ammonium sulfide. Let's take a look at the rules. Rule 1, does it have a nitrate, acetate, or chlorate? Nope. Rule 2, does it have an alkali metal ion or ammonium cation? Yup. So it's soluble. That's going to be AQ. And this is an example of why you stop reading. If you were to keep reading for number 4, you would get all the way down to rule 6, and you would see that sulfide, and you say, oh, it's insoluble. But you don't get to rule 6 because you stopped at rule 2. Hopefully that makes sense. Speaking of sulfides, Number 5, here we go. Iron 2 sulfide. Rule 1. Does it have a nitrate, acetate, or chlorate? Nope. Rule 2. Does it have an alkali metal ion or ammonium cation? Nope. Rule 3. Does it have a chloride, bromide, or iodide? Nope. Rule 4. Does it have a sulfate? Sulfate's SO4 2 minus. This is just S2 minus, a sulfide. Rule 5. Does it have a hydroxide? Rule 6. Does it have a sulfide, carbonate, chromate, or phosphate? It's got a sulfide. We changed this to insoluble. That guy is a solid. That's insoluble. Make it all the way to rule 6. Speaking of 6s, let's look at number 6. Barium phosphate. Rule 1, no nitrate, acetate, or chlorate. Rule 2, no alkali metal ion or ammonium cation. Rule 3, right? No chloride, bromide, or iodide. Rule 4, no sulfate. Rule 5, no hydroxide. Rule 6, we got a phosphate, folks. Rule 6 says sulfide, carbonate, chromate, and phosphate salts are insoluble. That's a phosphate salt. That is insoluble. We write an S for solid. That guy would stay a solid. Awesome. Any questions on how we did any of those? You do not have to memorize the solubility rules. I will give you a copy of the solubility rules. You do not have to memorize it.